talk about optimization and learning.
Okay. So it's a pleasure to be here. This is not supposed to turn on my volume, right? It's just a recording. Okay. So can you hear me in the back? Is this fine? Yeah, so I'll talk about something which a theoretical result. I've been thinking about it. It's motivated by practice, but this is a theoretical result which has motivated me for some time. And that's the computational relationship between online learning and optimization. Hello. And this is a joint work with my student Tomer Koren, who is at the Technion. And hi. So usually I like to start my talks with one slide. You know, I'm going to talk about matrix completion or linear separation or something very basic. But this is kind of a philosophical question, so I have to set up everything first, and that will take me a few slides. So 8 slides I counted. So please bear with me while I set up. And after that, the question should be clear, and also maybe the answer.
Is this one of the 8 or the 8 more?
This is one of the 8.
Okay.
Yeah.
I feel better already.
Okay. So yeah. So any course in machine learning should start. I don't know if it starts. Should start with statistical learning theory. This is the definition. And in this setting, we have a distribution. So nature is modeled as a distribution over the world, where the distribution is over features and labels. And the labels are 0, 1. And then we have a learner that sees all of the, can sample from this distribution IID, and produces a hypothesis, which is a mapping from the feature vectors to 0, 1. And that hypothesis belongs to hypothesis class, which we note by the letter big H here, which is a subset of all mappings from features to 0, 1. And the definition says that a concept is learnable if there is an algorithm that sees polynomially many examples in epsilon and delta for every epsilon and delta, and also polynomial in the size of the hypothesis class, such that with high probability, probability 1 minus delta, the error, it produces a hypothesis from the hypothesis class that has low error at most epsilon on the unobserved entire distribution. So, so this is the definition of the error, just the expected. If I draw one more example from the distribution, it is the probability that our hypothesis will be correct on it. And the main issue here is, of course, the number of samples that you need to see in order to produce this hypothesis. And that statistical learning theory says it has to be polynomial in this epsilon parameter and the probability of success, and also the size of the hypothesis class. So the size of a finite hypothesis class is defined to be logarithm of its cardinality, and that's the number of bits to address any hypothesis. And also, Vapnik talked about infinite hypothesis classes, in which case this generalizes to the VC dimension. I'm not going to talk about infinite hypothesis classes at all. But log H is the VC dimension of a finite hypothesis class.
Algorithm is the efficient algorithm or just any algorithm?
So Valiant in 84 talked about efficiency. And so he said defined probably approximately correct learning, PAC learning. And it's exactly the same thing, but also the algorithm that produces the hypothesis must run in polynomial time in M. So that's the whole distinction between statistical and computational learning theory. So how many of you have seen this before, this definition before? Okay, very good. So almost everyone. And the fundamental theorem of statistical learning, which is due to Vapnik from the 70s, says the following. It says that every realizable concept, one that we can actually learn, we can get the error to be as close to 0 as we want, is learnable in time which is polynomial in the size of the hypothesis class, so in log H. So how is it done? It's done by taking this M poly epsilon delta log H samples and computing the best hypothesis. We said we should have a slide, especially for you, if you come later, I think we didn't do anything so far.
Sandwich for me too.
You can have this one. So yeah, so this is called the ERM, the empirical risk minimizer, which is the hypothesis that minimizes the error over the sample that we took. Just take M samples, minimize the error on it. That is one particular hypothesis, maybe more. And Vapnik proved that this ERM has actually generalization error less than epsilon. For every hypothesis class with finite VC dimension. So this is the first maybe 3 lectures of a course in machine learning. Realizable means that you can actually learn the class. So the error can be indeed smaller than epsilon. Otherwise, people talk about agnostic learning and so on. Not important for this talk.
You have to iterate over the entire hypothesis class.
So what you have to do, so what you have to do is compute this argmin. You have to compute it. And sometimes you have to iterate over everything. Sometimes you have to solve an optimization problem. For example, if you want to find a hyperplane that separates vectors on one side and on the other side, you don't have to go through all possible hyperplanes, you solve a linear program. So
I think that story lock is the time of knowledge.
Yeah, time, that's not time, that has to do with
Samples.
sample size, right?
Right. So that is the sample size. And if you can, so in the Oracle model, if you can optimize efficiently, it costs you 1 to optimize, then the time is log-age. You sample log-age times, you call an optimization procedure, and you learned.
Call it sample.
Right. I prefer to call it time because, but okay, you can think of it. It's time in the Oracle model, in the optimization Oracle model. So if you think about it, so this establishes a connection between optimization and statistical learning because you sample log-n samples, you have an efficient optimization procedure, and that's it. You can learn. You can learn efficiently in the statistical model. Okay. Right. So this was done in 70 or 71, and I want to talk about a similar relationship or a similar question. Suppose we can optimize in the same way. We can find a hypothesis efficiently that minimizes the empirical error or error in some form. Can we perform online learning in games? And I will define now what it means. Okay. So just to stress, like Bob was saying, so sometimes this problem is NP hard, but many times, even for non-convex problems, we have an efficient Oracle. We can find the best spanning tree in a graph that fits weights and so on. So there are many, many interesting algorithms that can be applied to this problem and give efficient learning algorithms. Okay? So far? Right. So this is the question I want to address. And before I address it, I want to say something about why online learning in games is interesting.
Only if you don't want it.
So many times, so statistical learning is fundamental, of course, but many times it's doesn't fit the problems that we want to solve in practice because the environment is non-stochastic. As a matter of fact, I would say it is never stochastic. So for many interesting applications such as spam filtering and recommendation systems and so on, there is no reason to believe that the data comes from a distribution. And if it is definitely not IID, right? So that's why online learning was developed to tackle this kind of...
You mean that, I'm not sure I understand what you're saying. Because if it's stationary, you can always call it a distribution. So you mean because it may change over time?
It's adaptive. Think of spam, for example. So you build a filter, and then the malicious spammer is going to change his whatever he's doing. So it changes over time. Right. And right, so online learning is sort of become very popular in recent years, and it gives stronger theoretical guarantees. You can prove formally, I will do it in a minute, that online learning implies statistical learning, and it is useful because it has a game theory connection and insightful connections to optimization. So many things that came out of this study, such as sublinear optimization and projection-free methods, zero-order optimization, and so on. There is the whole connection to bandits, multi-armed bandits, decision theory, which is present in online learning, but not so present in statistical learning. And it is very well studied. So in recent years, in the last 10 years maybe, if you look at conferences of learning theory, then 30–40% of the papers deal with online learning, and it's not like the rest are statistical learning. This is by far the largest group of papers that people have been studied. So that's why it's an important framework. Another reason, which I sort of glanced over, online learning is many times more efficient because you see one example and then you update your hypothesis. Many times you can do it much more efficiently than training a classifier altogether. So this is, many times these are techniques of choice when you have, at Google and so on, when you have these huge data sets. So let me define online learning, and I have to start with the notion of zero-sum game, which is, this of course everyone has seen. This is more basic maybe than statistical learning theory. So zero-sum game, we have two players, a row and a column player. By analogy to statistical learning, I call the row player strategies hypotheses, and denote the number of possible hypotheses as n. And then we have examples. These are played by the column player, and there can be infinitely many examples. And the loss, so for every hypothesis and an example, there is a loss between 0 and 1, which is whether the hypothesis got that particular example right or not. And now we can define what it means to learn in games. So you can think of an iterative scenario in which the player picks a hypothesis in the class, and then the adversary responds with an example. But there is no distribution here. This can be completely adversarial. And then the player suffers a loss. And your goal now, so there is no stochastic meaning of error. This is an adversarial meaning of error. We look at regret, or average regret. So that's going to be the average loss that our algorithm has suffered as compared to the loss he would have suffered had he chosen the best fixed hypothesis in hindsight. And we want this to converge to 0. So if you have never seen this before, this is striking that it can be done, but it can be done. That's why things are so...
That's a single hypothesis, though. That's a pure strategy, if you will, as opposed to a mixed strategy.
Exactly. So you have a dynamic strategy, and you want to compete with the best fixed strategy. So unlike competitive analysis, which Bob has been doing, so in competitive analysis, you try to compete with a changing strategy, but here we're dealing with a fixed one.
The only reason you can do something.
This is the only reason you can do it. And as a matter of fact, it implies, when you think of if the examples are coming from a distribution, this implies generalization error, because the fixed hypothesis in hindsight is going to be the best learnable hypothesis, and you get from this, using concentration bounds, statistical learning. So this has a very nice analogy to statistical learning.
Just to be clear, so
Yeah.
the fixed one has to be a pure strategy, or it could be a mixed strategy that you're forced to use every time the same?
Okay, that's a good question. So the strategy of the player I think of as the role player, the one that plays the hypotheses, he can play mixed strategies too. And in that case, you measure the expected average regret. This is a good point. Okay?
But the adversary, that's a pure strategy. That's
The adversary, yeah, that's a, yeah, well, strictly speaking, he can also play distribution, and it's the usual case of randomized algorithms that if both players play distributions, they cannot see the coin tosses of the other. They can see the distribution, but not the coin tosses of the other player. So just the standard randomized algorithm setting. Okay, what is an optimization oracle in this case? So in the statistical learning, just the best hypothesis for the sample. So here you can generalize this and say an optimization oracle is one that takes a multi-set of examples, or if you want a distribution of examples, and returns the best hypothesis for it. And now the analogous question is, to the one we asked, that Vapnik asked in statistical learning, is can we learn in games efficiently? So let's say that we have this general setting, and we have an optimization oracle because we know something about the problem. Can we achieve regret, which is non-trivial, let's say less than 1/4 or any constant you want, in time which is logarithmic in the number of hypotheses, or iterations which is logarithmic in the number of hypotheses, if you prefer, like Sanjeev was saying. Okay.
Now, the optimization oracle can only do that thing, or can you make it do other optimizations?
Only do that thing.
That precise thing, j equals 1 to k.
That's it. That's the only thing you can do. You can give him any distribution over examples,
Yeah.
and it can return the best hypothesis in the class.
Oh,
so
so
just
that's different from, I see, okay.
so a distribution can be represented as a multi-set over examples.
that log in, that's t there. So after time t, the player picks a fixed strategy, and that's the one that then gives him.
Okay, that's a good question. So, right. So this average regret is well defined for every t, right? Now, we want this to be less than 1/4 in total time. Now, you can run in, I don't know how many iterations you want and do 0 computation, or you can do a lot of computation in 1 iteration. I don't care. But just in this amount of computation, I want you to produce regret less than 1/4. You can spread it out over many iterations, or you can do it concentrated over a few iterations. Okay? Yeah?
What's the sigma latency?
Here?
Yeah.
Oh, yeah, this is unfortunate mistake. So there should be no sigma t. Okay. Yeah. Or put, so okay, put this sigma t inside. That will be the more precise.
Where is the brackets?
Bracket has to go here, okay? That's the shortest Hamming distance is to take this bracket and moving here, okay?
No, but the sigma is from T from 1 to big T?
To big T, yes.
Oh,
Okay. So this is the question. Who guesses it can be done? Who thinks it can be done? I didn't look.
Again, I don't understand what you're
The
asking.
more interesting answer is that yes, so you gotta bet on yes.
Okay.
But when
You're an
say-
optimist.
When you say it can be learned, you mean is this oracle, if you just use that as your answer at every step, does that give you lower error? Or
No,
can
doesn't.
you use that in
So
some
this is known.
other-
This is known not to work actually,
Okay.
because what can happen? You can have just two hypotheses.
What was this suggestion?
You just use the optimization oracle and you output that as your
Follow the lead.
hypothesis.
Yeah. So actually, this is a great question. So in the statistical setting, this does work. That's what Vapnik proved. And here, it's an adversarial case. So the adversary can see, oh, you're going to use this best in hindsight. I'm going to make him suffer in the next example, and so on. So
But if you use it cleverly, okay, you can.
that's the question. Can you use it cleverly? Okay.
Efficiently, you now mean with the oracle as the
Yeah.
oracle, because
This-
you can't even learn efficiently in classical.
Absolutely correct. So the computation model is that the Turing machine has some kind of oracle. It can write a distribution on a separate tape and then ask, oracle, give me the best hypothesis for this distribution. And then the oracle gives you the hypothesis. This is the model. I don't want to write all this on the board, but you guys get my meaning. Okay, so we have one guess of yes. Then I didn't hear too many proposals. So
But do this multiplicative way. Multiplicative.
very good. So let's think about Bernard's suggestion. I might allow myself to go a little bit over time if there are many questions. So, right. So Bernard says, okay, what if we give weights to all the strategies in the hypothesis class and play multiplicative updates? And we know the regret of multiplicative update method is logarithmic in the number of hypotheses. But the running time, you're going to spread n weights, right? And then you have to update them. So your running time per iteration is going to be n. That's already much, much more than the log n that you're allowed. Okay.
So there is an element of time here, not just oracle complexity. But somehow that computation time is...
Well, we abstracted it out.
Multiplicative reweighting would work, it's just too slow.
Exactly so.
But that's
Exactly so.
time, not oracle complexity.
No, so the model again, Turing machine with access to an oracle. So,
But
right?
This oracle
I
at
see.
least takes n time, right?
Sorry?
This oracle at least takes n time.
No, why? Not necessarily. Let's say you want to compute the best hyperplane given a set of data, right? You can do it using linear programming. So the dimensionality, you're going to be polynomial in the dimension of the space, right?
Capital H,
Right? Okay. I'm happy there are these questions. I just want to make sure this question is clear now, because at this point it should be clear. So this is the question I'm asking.
So capital A is something like exponential.
Sorry?
Capital A is something like exponential.
Yeah, that's the way you should think of it. So describing a hypothesis is logarithmic in the number of bits. That's the VC dimension. And then capital H, the cardinality is exponential in that. That's like, it's not, exponential of the VC dimension. Okay?
So I guess another way to ask Bernard's question is there a sampling version of
This is exactly,
multiple weights?
this is the question. Yeah, you can think of this as the question. And there have been attempts in this way. People who thought about a smooth fictitious play and, or follow the perturb leader and things like that. But it's not, all these methods, I will refer to them in the coming slides. They don't work.
Just to be totally clear, time is not little t. T is the number of iterations.
T is a number of, small t is,
Time really is computation time. If you
Yeah.
assume oracles take a
yeah,
long time.
yes, absolutely, yeah. So the guarantee I'm looking for is regret, average regret to be less than a constant. That corresponds to solving an equilibrium in zero-sum games. I will show this. Okay. So this is the analog of the, right, so similar to the fundamental theorem of statistical learning, this is what we're looking for. And now the first thing I want to say is why this is interesting. And you know, this is a slide you don't see coming up often in theory talks, but I think it's really important. You should justify why what you're doing is interesting. So does anyone think it's not interesting? No. First I will say.
You're a big guy. We don't want to.
No, I want to justify this. Okay, so right. So this is a basic question in learning. I argue it's a basic question, and it's very practical. So there have been many, as I said, there are many papers in COLT. Right? What are they all doing? If we had the fundamental theorem of statistical learning, we didn't need all these papers, right? So people try to come up with general methodologies for converting optimization into online learning. And there are many such frameworks, like what Bernard and Sanjeev were saying. There is follow the perturb leader, you add perturbation and invoke the oracle, or you exploit some convexity in the structure of the problem, and so on. So there have been many attempts, contextual bandits and so on. I really listed only a very few number of attempts to do exactly that. And lacking a general methodology, there have been many other papers that say, okay, we don't have a general methodology. Let's study one particular non-convex problem and try to minimize regret for it. For example, a submodular optimization, or it doesn't have a convex structure, right? So, or you want to learn rotations or permutations or eigenvectors. So eigenvectors, for example, it's a non-convex problem. You can still solve it efficiently. You can compute an eigenvector efficiently, but it doesn't have any convex structure. So there are many papers, and some of them of my own, that do something very specific for these problems. And it would be a shame if it were to all go to waste and we had a general technique of doing this conversion. Or maybe not a shame, maybe it would be great. So that's why I think
There will be huge regret.
Yeah, that will be regret on my part, yeah. So, right. So now I'm ready to, so if there are no arguments, if I would give this in my technical department, people would argue about this slide now for 5 minutes.
That's Israel.
No, it's just a different, it's not a CS, it's some other culture, like OR, right? People would argue about the importance, which is very important too, to argue about the importance of the result. So good. So here are the results.
What's the argument that it's not important?
You ruined my, that it's not important? I don't know. I mean, I think it's important. So, okay. Yeah. Right. So here's the first result. The first result says it cannot be done. So actually, in this optimization oracle model, then any online learning algorithm with average regret less than 1/4, and I don't care how many iterations it performed, has to run in time root of n. Okay, so exponentially more than statistical learning. So that's a bad thing, but also a good thing. So all these previous papers are don't need to be thrown to the trash can. And then you might ask, so there has been a proposal to use multiplicative updates. That would be O of n time, right? But turns out this root n is tight. So you can actually do something with your optimization oracle. It's not some kind of useless thing. You can use it to improve quadratically the running time. And this actually is important. This quadratic improvement is important. So if you have, in many cases, you have many hypotheses, but not that many that you can suffer this quadratic.
How many logs are hidden in the tilde there?
1 log, and a constant of 2 maybe also. You know, so generally in this literature, the constants are very small.
The assumption is what for the lower bound? Complexity assumption is what? P is not equal to empty, or just information theory?
Information theory. No assumptions. This is assumption free.
The number of samples.
Even the number of samples must be.
Just the number of rounds you have to play. That's square root of n.
No, that's not the lower bound. No, the number of rounds can be log n, but then the computation you have to perform has to be at least square root of n.
But when you say computation, you mean the number of oracle calls, the number of optimization calls.
Yeah, so the number of oracle calls plus the running time. So the Turing machine has to run in this model that I defined.
But it can't come from computation. It has to come
it's information, purely information theory. I will show you exactly where it comes from. It's information theoretic. And so a corollary is that you can compute approximately the equilibrium in zero-sum games in root and time if you have a best response oracle. And that's, again, quadratic improvement to previous things that have been done that have been n, not root n.
Okay. Is this a statement about any instance of this general problem, or this is a statement about there exists a hard instance of this general problem that runs badly?
No, any instance. So there are problems. Right. Like if your problem has a convex structure, low-dimensional convex structure, you can actually beat this completely. You can get log n. So if under some special structures, you can do much better.
Okay, so there exist bad instances.
Yes, but you don't have a general reduction. And this is very important to have a general reduction, but you can't.
But some of those previous papers actually do much better than this in specific cases.
Absolutely, yes. So all these, I don't know, hundreds of papers did something, but.
So if you're allowed, the learner is allowed to output the distribution on hypothesis, then it becomes easy. That's what you're saying?
No, still doesn't become easy.
So what do you mean by convex structure?
If your hypotheses are hyperplanes in R to the D, and you discretize the unit ball, then you have 2 to the D, or I don't know, 1 over epsilon to the D hypotheses, but you can still solve it in D time. You can still get D regret and D computation time.
But if I'm allowing arbitrary distributions on hypothesis, then it becomes convex.
It becomes, but it becomes high-dimensional convex. So I said low-dimensional. So I said only if you have low-dimensional convex structure. High-dimensional convex structure doesn't help at all.
But
right.
distribution mean mixture of hypotheses?
Yeah.
Oh,
It's the distribution.
Yeah, that's not the thing. That would be trivial. That's not the, doesn't help. So
the last corollary is just about finding equilibrium games.
Yeah.
But you can do that with linear programming, right? So
you can do it in, so let's say you have an n by n game,
Yeah.
and that is of course equivalent to linear programming.
Yeah.
You can solve a linear program in, I don't know, n cube or whatever time, some kind of polynomial in n,
Yeah.
right? And
One time it's linear programming.
Yeah,
That's
it's
one call in your model, right?
no. Okay, let's forget the zero-sum game for now. We'll get to it. Just I can explain. So the log n is efficient, not n. Let me get back to it later on. Okay. So let me start with this first thing. Lower bound. Okay. So how do we prove a lower bound? Well, so Zev asked correctly. I mean, it's or someone asked. This is an information lower bound, right? So we do it by reduction to another problem. I mean, if you are Sanjeev, you can prove the PCP theorem. But otherwise, you have to do a reduction to another problem. And here is the...
Is a reduction.
Sorry?
PCP theorem is a reduction.
You know, I mean that it's not... So this is much easier than the PCP theorem. So here is the setting that we borrow from Aldous. So he's a probabilist. And he talked about distributions over the hypercube. And defined the following distribution. So think of taking the discrete hypercube and starting from the uniform distribution. And then you perform a random walk. So random walk meaning that so it's a d-dimensional, there are 2 to the d vertices. You pick one at random, then you go to a neighbor. There are only d neighbors, so with Hamming distance 1. You go to it in random and continue. And the function is going to be the hitting time, the first time you reach a vertex, starting from the origin. This is a distribution over functions. And this distribution over functions has a very interesting properties. So first of all, this has only one single local minimum. So such functions that have a global minimum is same as local minimum, they are called unimodular. I think Amirali, correct me if I'm wrong, in optimization. It's a unimodular function. And this function is unimodular. So can anyone see why there is only one minimum for this, local minimum for this function? Sorry?
You start somewhere.
Yeah, so if you are at some point, right, what does it mean that all your vertices have a smaller value? Well, you came from somewhere to this vertex. Or either you started there, in which case it is 0, or you came from somewhere, and then some other vertex needs to have a lower value. So these functions, all of them have a single local minimum.
You
And
said starting from uniform distribution.
yeah. Sorry? So any function coming from that distribution has this property that has a single local minimum. You start from a uniform distribution and perform a random walk. This gives you a distribution over functions.
The hitting time.
Yes. And any element from that distribution has the property that it has a unique local
Okay,
minimum.
fine. It's a mixture of functions.
Yeah.
Okay.
And
indexed by the starting point, right?
Yeah.
Yeah. Yeah. And second question is, how much time does it take to find the local minimum, global minimum? So let's say I give you Oracle access to this function.
That's the randomness.
Yeah.
So this function is defined on the hypercube?
Yeah. Discrete function.
Okay, and the value at the corner is the hitting time if you start at a random point.
So here is, yes. So think, this is how you generate a member of this distribution. Pick a vertex uniformly at random, give it value 0, then you start going around by a random walk, and every time you hit a new vertex, you keep a clock. The value of that vertex is the clock. So this generates one function from that distribution. They all have a single local minimum, and furthermore, there is something interesting that has to be said about optimization for these functions. How do you find the minimum? You can go over all the vertices, right? It will take you 2 to the d time, and find. And find, I mean, you have Oracle access. You can ask, this vertex, what is the value of it? So, and you get an answer.
Follow the numbers back, you follow the...
Good. So using this idea, you can do it a bit better, right? So how quickly can you find the local minimum?
Typically, it should be n, closer to n. If you start in a random vertex, it should be roughly n. Right?
Yes, that's true.
You can revisit states, right? So you have an extra log or something.
Yeah, well, so that will only improve by a bit, right? So you have 2 to the d, 2 to the d, and so you can do 2 to the d, that's and a bit better. But you can do root 2 to the d, okay? How can you do root 2 to the d? You sample root 2 to the d vertices, take the minimum one from all of them, and then follow it backwards until the origin, right? So on expectation, you're going to hit the order statistic root n from the below, and then the path to the minimum is going to be root 2 to the d. It's called local cell. This is clear? So you can do root 2 to the d, and that's interesting already, just by this local global structure. And this is an interesting theorem that Aldous proved and Aronson improved on, that any algorithm that can distinguish between even an odd minimum vertex name, that can find the minimum vertex, with probability bigger than 2/3, must run in time at least root 2 to the d. Okay. So this is obviously, who asked, I don't remember, this is an information theoretic argument, because in root 2 to the d, you don't even get to see the entire cube. So there are no assumptions here, no computational assumptions. Okay. So let's see how.
Are you going to sketch this proof, or this?
No, this is an impossible proof to sketch. This is a very complicated proof, and that's why Aronson, I don't know, 20 years later, came up with a quantum simplification. I don't know how simpler it is, but it's quantum simplification to this proof. So
this is an average case law one, so it's for a random function, even if you...
yes. So you sample uniformly at random from this distribution over functions, give it to an algorithm. And the claim is that this algorithm, if it wants to be correct with probability at least 1/2 or 2/3, it has to run in this much time. Okay, what is the relation between this and what we asked?
What's the query, what's the oracle here?
Value oracle.
Value of f of e.
Yeah. Right, so what is the relationship between this and games? That's what I want to show. And here is how we used his construction to create a game, an instance of online learning. So, right, so n is going to be 2 to the d, and we have a name, so we create a zero-sum game, and we have this many strategies, all vertices here and here. And the question is f of v odd or even? So f of v, the vertex name is it odd, just find, something like find the minimum vertex, and based upon it, we give a value to the equilibrium, which is 1/4 or 3/4, if it's odd or even. Okay, so now you can check that this game, this is a very simple game. It has only one pure equilibrium, and this is the equilibrium. Okay, so from any other pure strategies, you're going to go down, down, down this matrix until you hit the equilibrium. And right, And the definition of the game is the following. We give the ij entry is going to be 0 or 1, depending on whether f of I is bigger than f of j or not. Okay. So what do I need to show for this reduction to work? Obviously, I can't build this whole matrix because that will take too much time. It's going to take 2 to the d time. But I need to construct, given an Aldous function, I want to construct a value and optimization oracle for the game. And that will show that I cannot minimize regret, because if I minimize regret, I will be able to find this equilibrium much faster than I should, and then I'm able to solve Aldous's problem much faster than I should, and that's a contradiction to what he proved. Okay. Okay. Questions?
How did he come up with this problem in the first place? What was the original context?
He was interested in local search. So think that you want to do an optimization, you want to solve an optimization problem. And all you can do is query local things, or you can optimize locally. You can find a neighbor that is better than yourself. And these functions that he described exactly have this property and nothing else, miraculously nothing else. So he really captured the value of local search very, very well. Okay, so
he uses some complicated graph for this, not the hypercube.
you're asking about his proof?
Yeah, you draw the graph there.
So no, which graph? No, this is his cube. He just used
our cube.
hypercube.
Okay.
Yeah, just hypercube.
Okay.
Which is very nice because you can always, given a vertex, you know all its neighbors in polynomial time, right, in d time. Very explicit, very beautiful construction, and just fits immediately to what we want.
I mean, Aldous or Scott, I mean, which one, when you say he?
Aldous. Aldous did the whole thing, then Scott simplified it and improved the constants.
For different graphs, is it a different, use a different graph? No.
I don't know, but I think it's much less interesting if you use a different graph. This really captures what you want to do. So in terms of optimization and also in terms of, we'll see this learning. Because you need some way to access the neighbors, right? If you want to do local search, you need an efficient way.
Many other graphs you can access the neighbors.
Yeah, okay. But this is the nicest, right? You just, given a vertex, you know all the neighbors. Just take the Hamming distance one. Okay, so I need to show you how to construct a value oracle and an optimization oracle efficiently, because that's the main issue of the reduction. So the value oracle, this is easy, right? If someone queries what is the value for that strategy, for a pair of strategies, I can just look up f twice, and I know the answer, right? In optimization oracle, I need to be able to compute the best strategy given a set of column strategies. I need to be able to compute the row strategies efficiently. And here is the observation. So given a set of column strategies, what is the best row strategy for them? Well, there are many. All those that are below this line here, right? Because this is a distribution over columns. If I pick this row here, then the value that I get is 0, and I want to minimize value. Every row below that gets 0. So all of these rows give 0, and I'm just going to pick the first row that returns a value of 0. How to compute this efficiently? So this is not that trivial. You need some kind of data structure, because you need to be able. So the answer is you just take the support of the columns and take the maximum guy in the support plus 1. That is the answer to the optimization oracle. I just showed you by picture. And to compute it efficiently, you need some data structure that can take a set of indices and compute the max in constant time or logarithmic time, right? So a heap or something like that. Okay. All right. So that's pretty much the lower bound. I mean, there are many details to flush out. I'm not going to do it. Okay. And now I want to spend time on this. So the main technical difficulty is theorem 2, actually, which is that the optimization oracle does give you something. You can still improve quadratically on the running time compared to doing the benign thing of multiplicative updates. So how much time? I don't have that. No, I have little time. I have like, how much, 10 or 15 minutes?
No, we started late. Go.
Okay.
Half an hour?
Can I ask a question about the adversary?
Yeah, I didn't get it either.
Sorry?
So there's the player playing online, and then there's this other guy called the adversary, whatever you call
Yeah.
that thing. Now that guy, to carry this strategy, we need exponential time in reality, because he's got to figure the hitting times and how it's going to work.
Oh,
I mean, if you actually wanted to have a human being do the columns, would they need exponential time to actually?
okay. So yeah, I don't want to look at exponentially many columns, right? I just want, so because that will just take too long. So, and I think, so the general gist of the things is this. I can create these efficient oracles, right? That they can query the function just once and return the minimum vertex given a set of columns, and also give you the value of a pair of things. Now, if you have an algorithm, you tell me that you can learn quickly in polynomial time, then I can run this algorithm against itself and compute efficiently and compute the equilibrium of the game, which will imply that you learn the minimum value of the function, which is a contradiction to what Aldous did. Is this answer what you're saying, or? Okay. Yeah. Okay, so now theorem 2, right? So I want to show that there exists a new algorithm that gets this new root n bound instead of n. This is based on technology from decision making. I'll try to do it very quickly, this part. So even though it's more heavyweight. So, right, so decision theory, right? I'm guessing that most of you have heard the multi-armed bandit problem. So that is a decision problem. You have every iteration, you have to pick an arm, and then you get to see a loss, which is 0, 1. And this loss is adversarially generated. And you repeat this again and again. Right, so the goal is to minimize regret. This is exactly the online learning scenario that I described, with only one difference: the feedback. All you get to see is the loss. You don't get to see anything else besides the loss, just one real number.
What did we see last time?
Sorry?
The previous model, what did we see?
In the previous model, you could potentially see anything you want by an oracle, but you just don't want to spend time maybe to see everything because there are too many strategies. So everything is potentially visible. Here, not even if you want to see, you're not allowed to. You're only allowed to see what you picked. Okay.
But in the previous case, you saw x, right?
So you see a loss, a real number, which is 0.
In the previous one, you also saw x, right?
The choice of the others.
Oh, the choice. Yeah, you can. Oh no. So, yeah. In this model, you don't get to see x.
In the previous one,
Yes. It's not that I'm just sort of I will just take this piece of technology and use it, so it doesn't really matter. I'm not going to relate this model to the previous one. Okay, and so here is a solution to this problem, which is called the XP3 algorithm by Auer, Chezabianchi, Freund, and Shapiri. And it's an instantiation of the multiplicative update method, which says the following: you give a weight to each arm, and then you choose. So the weights initially they're all 1 because you have no preference over them. And then you choose an arm with distribution proportional to these weights, because they define some kind of a distribution. And then you get to see a loss of the arm that you picked. And now you update the weights. So you only saw one arm. You cannot update what you didn't see. But the arm that you saw, you update exponentially according to the loss, scaled by a factor of the number of arms, in order to make everything work out. So this simple algorithm contains the following amazing guarantee. The regret goes to 0 at this rate, root of n over t. N is the number of arms, t is the time. And furthermore, the running time is constant, right? So all you have to do every iteration is update one weight. That's it. And of course, you have to resample. So maybe you need to maintain some kind of data structure for sampling, but that's also easy. Okay, and this is known to be tight also. So this is a very beautiful result. And the question is it good enough for us? Because the running time at least is very good, right? It's constant or logarithmic. So the running time is perfect. But it doesn't work for us. So what we're shooting for is something better. We're shooting for root of root n over t. Because we want this whole regret to be less than 1/4 after root n time or computation, if we spend O of 1 per iteration. Okay?
But why do you need the big root at the outside?
It doesn't have to be big root, but it turns out that this is the correct, this is tight. Yeah. A priori, you don't need it. But you can't do any better here and also here.
This problem should be much harder than the previous problem, right? Because you have a lot less information.
Yes, right. Here you mean?
No, the bandit problem should
bandit.
be much harder.
Very hard problem. But turns out that it's also, the same techniques are used in the full information in the bandit. This is one of the magic that happens in online learning, that you can really use less information and get nice bounds. So this is one of the advantages of online learning. You have these very simple algorithms. They use almost nothing, and they give you statistical guarantees. Okay. So a recap, right? So what are we trying to do? We're trying to learn in a game. We have these n strategies, and then we have examples, and iteratively we pick a strategy, and the adversary picks an example, and we get a loss. We're trying to minimize regret. This is the regret we're shooting for, and we have access to an optimization oracle. In this positive result, I'm going to restrict. Going to say this works even in a much less restrictive setting, that all I get to see is the best hypothesis so far. I don't even need the oracle. I just need one bit of information, or the best guy so far. And the goal is to have a running time which is polynomial in log n. Okay? Maybe, yeah, let's see how I with time. Right, so here is how it works.
Wait, I missed that. Yeah.
It's crucial. If you missed it, you can't understand anything. Maybe I'll go for 5 minutes, and then I'll recap, because I don't think I'll have time to go through the proof. But just the main idea.
So indeed, you get the square root n.
Yeah, exactly
for
that.
that bandit set.
Yes.
That's stronger than online, or is it?
Yeah.
It is strong.
Yeah.
The bandit result is sharp, so what is the difference?
Well, we have an optimization oracle. We have the additional bit of information. Who was the best guy so far?
Okay.
Okay, so here's the main idea, and this also bears resemblance to local search, the Aldous problem, which sort of, you don't really see the connection immediately, but there's also connection to the upper bound, so it seems. So what you do is the following. Well, we have access to the leaders, the guys who have been best so far, and we want to take advantage of it. Now, if there are many, many leaders, every time there is a new expert that is the best, then sampling is a good idea. You sample many experts, you're going to hit one of them that is pretty far off, right? And then if you follow him, you're doing pretty well.
It doesn't follow just from changing. I mean, only if there's density or something, right?
You need there to be a lot of, yes, you need there to be a lot of them.
Yeah.
So if you sample k balls from n bins or whatever, right? So you're going to hit the order statistic 1 over k. Now, if n is big, then you're going to do well. If n is small, you're not going to do well. And the other thing, and then there is another case, which corresponds to the local search. If there are few leaders, then we have to use the oracle. Because if there are few leaders, it means that our oracle will give them to us very quickly, and then we can sort of forget about all the rest and focus on them. That's the two cases. And how am I doing with time? Not so good. I'm not going to go over time. So how about this? I'll just sort of finish off, and then people that are interested can ask. I can give more details. Yeah, OK.
So show the algorithm. Yeah.
I will show the algorithm. OK, so this is the final algorithm. And it does the following thing. You take all the strategies a priori. You sample root n experts, hypotheses, and keep them on the side. Then you have log n sliding windows that are size 1, 2, 4, and so on up to root n. What does each of them do? It's written here? No. Each of them takes let's say this window, every time there is a new leader, it replaces what it has in the window, throws it out, and put a new guy in, and so on. And this guy has a window of 4, so every time there is a new leader, it throws out the oldest one, puts the new one in. And then each of these is an EXP, is bandit algorithm on the sliding window. Okay? So we have log n algorithms plus root n samples. And we run EXP3 on the bandit algorithm on everything, on root n plus log n. And that is it's pretty simple algorithm.
What's the algorithm again? The log n algorithms? Describe again.
These?
Yeah.
These are bandit algorithms applied only to leaders. Only to what came from the optimization oracle. You take what came from the optimization oracle and you apply and so far.
In all the previous rounds.
Yeah, but you sort of restrict attention to only to 1 or only to 2 or only to, so sort of in logarithmic scale. And then you apply.
That's the best, and that's the 2 next best or something?
Recent. Most recent, 2 most recent, and so on. And each of them you try to learn inside the set, and then you apply another algorithm on top of everything. So it's a pretty efficient algorithm, I would say. It's not a terrible thing. And the guarantee is this, that with probability 1 minus delta for any sequence, adversarial sequence, the regret is root of root n over t log 1 over delta. So the best you can do, given the lower bound, this is the best you can do.
Can you say a little bit more about this? I mean, are you trying to guess when in the past the best guy, the best leader has appeared, and you're just trying to take?
I can, but then you guys are going to blame Bernard for me being late, okay? So here's the, okay, so here is why. What happens is, these leaders come by, right? And you you have windows that keep sort of the latest guys. And now, the main definition is when someone dies. What does it mean for someone to die? It means he never ever is a leader again. Okay? Now, think of the following argument. You have a set of leaders, and let's look in the future when all of them die.
You
Okay?
should call it retire, because I think it's very pessimistic.
Okay. Okay. So the argument is.
Especially it's not the North Korean leader, right?
Am I not allowed?
Otherwise, all of this will be crashing around.
Right. Okay, point taken. So there is, in all these windows, there is a correct size window that will capture all of them, plus all the new leaders that will appear during this time window until all of these retire. Okay? And then what do we get in this window? We get a guarantee that we're as good as the best one here, which when he retires, he's the best one. What does it mean that he retired? Here he is the best. We only need to compete with him. And from here on, you can do the same argument again and again, but every time it's a different size of window. That's it. So it's not a complicated argument. Okay, so Bernard is to blame for maybe at least 2 minutes. Good, now wake up. And now, zero-sum games. So Amirali asked about zero-sum games. And zero-sum game, the solution concept is an equilibrium, which is a pair of distributions over the row and column strategies such that each one is optimal with respect to the other, right? You cannot, given a row strategy, you don't want to change your distribution because you're not going to do any better than you are now. And indeed, right, so people have been asking the question, is this efficiently computable? And are there efficient, more interesting maybe, are there efficient strategies that if you play one against the other, they're going to converge to this equilibrium? Right. So yeah, as Amirali pointed correctly, this is equivalent to linear programming. You can solve a linear program.
The problem is the input is exponential.
Right. The input is huge. Right. You have many, many strategies. You don't want to solve a linear program here. So people have looked at other approaches. And one other approach by Grigoriadis and Katia and also by Freund and Shapiri is to play learning algorithms one against the other. So they get, this is a very striking result actually, because the input size here is n by n. You have an n squared input size, but you can still solve the equilibrium in time of n. So a square root of the input size. How? By playing multiplicative weights one against the other. They converge to the equilibrium. And this is tight. You cannot do any better. Okay? And people have thought, okay, what happens if we have players that have a bit more power? Because this is tight. So what we show, this is a corollary, a very simple corollary of what I described, is that you can actually do it now in root n. So this is fourth root of the input size, and this is tight, if you can also compute the best response. Okay. So that's the implication to gains. So yeah, back to the question I started off from today. Is optimization computational equivalent to online learning? So yeah, I just had to put this because I have an ongoing debate with Sanjeev about online versus statistical learning. And online learning is a much better approach, but that's not what I showed today. But computationally, it is exponentially harder if you model it according to the optimization Oracle framework. So you can do optimization, okay. Statistically, it guarantees you can learn, but online learning doesn't guarantee you can learn. But it still helps you. So being able to optimize over the hypothesis class gives you a quadratic speed up in terms of what you can attain. So I'll finish here. Thank you very much.
Reconstruction, you said something about that.
It will take a long time. Yeah, reconstruction. So, right. So many times, statisticians take the following approach. Let's say to learn matrix completion. Let's say you want to learn a matrix, and you observe. This is useful for predicting movie preferences and so on. So you observe some entries of the matrix, and you want to predict the others, right? Now, statisticians take the following approach, which I think is not wrong, is not correct. But they take the following approach. They say, OK, there is an underlying matrix, and then there is noise, and we get to see some observations. And now we want to recover the matrix, right? And this can be done under certain assumptions on the matrix, and sometimes it can be done efficiently. The non-reconstructive approach is to say the following. I don't care if there's an underlying matrix or not. All I want to do is be correct in my predictions. So it's a matrix or it's some other thing, I don't care. I want to be correct. Every time you ask me a question, what is this entry here? I want to give you a correct prediction. And here you can use a different set of techniques coming from the online world by iteratively modifying a matrix or some more general even creature that will give you good bounds in terms of regret. Okay.
If there's no underlying matrix, how do you know you're correct? What do you compare?
You can compare loss.
So there is a true one. I mean, to know if you infer a loss, there is an underlying matrix. No?
Okay.
The matrix completion.
Well, the underlying matrix, many times it is assumed that it has low rank, and it has properties such as incoherence. Okay.
So you say,
And I just want to compete with the best matrix from a given class. And this class doesn't have to be low rank, doesn't have to be incoherent, it doesn't have to be anything. That is the competitive approach to learning. So it's more general, and this discussion is kind of off topic, but you can definitely model things in terms of loss, iterative loss minimization, instead of trying to reconstruct. Okay. Questions? Okay, thank you. Thank you.
Oh, sorry. So this optimization objective could be non-convex or something.
Could be non-convex.
That you cannot solve in polylog in time. Right?
Yeah.
Do we know any example when it is really can be solved in polylog?
Of course we do.
But in the online setting we still have this computational difficulty.
Yeah. So take, like, for example, a spanning tree example, right? So your hypothesis class is a set of all spanning trees in a graph. There are exponentially many. And then the loss is given by iteratively, you have weights on a graph, and your loss is going to be the sum of weights on your spanning tree. Minimum spanning tree. You can solve the minimum spanning tree question offline, efficiently, right? You don't need to go over all the spanning trees. But how do you minimize regret in this setting? Not clear. Yeah. Okay?
Is there a connection with Grover's algorithm?
Grover, is that the basis kind of?
I mean, why
Quantum.
did Scott do this with more complex? I mean,
That was Scott's motivation.
can you interpret Grover's algorithm in terms of online learning? in an Oracle model.
One-line quantum law.
Yeah.
Yeah, unfortunately, I just don't know enough quantum machinery to answer this. I remember I learned Grover. Shamefully, I learned it, but I forgot. But what Scott did, basically, I can say what Scott did. So he took the same construction and proved. So Aldous proved a lower bound, which is of the form what you can see in here. But it's of the form the following. So for every epsilon, the running time is O of 2 to the d minus epsilon square root. That's what Aldous proved. And Scott improved it to root of 2 to the d over d squared, something like that. So it's a better bound in terms of d. And it also implies actually tighter bounds for what we're interested in. But it's just a matter of tighter bounds and a different analysis. So there's nothing fundamentally, it's the same exact setting of randomized functions over the hypercube and so on. Yeah. Okay, thanks.